So now we are on chapter 3. We've finished chapter 1 and 2, and all that's left is chapter 3 for the midterm. Now on your calendar it says that for the midterm we're not going to complete chapter 3. We're going to cover all the way to chapter 3.4 or section 3.4 for the midterm. So it is scheduled for 3.4, but it can change depending on the pacing that we're going. I left days on the calendar just in case of weather or any sort of storm that may or may not happen. So, chapter 3, in particular, chapter 3 is called Polynomials and Rational Functions. I'm just going to call it polynomials, and we have discussed what a polynomial is. Let me write that, polynomial. Now, the issue about our definition earlier, polynomials were defined very loosely. Polynomials were defined to have more than one term, an expression with more than one term. But this time, we're going to see them as functions. We're not just going to see them as expressions or anything. Now we're going to relate them back to machines. So this means, in particular, we're going to have more precise definitions, and the training wheels are kind of off. So here is the definition for a polynomial function. A polynomial function definition of degree n. I am assuming you guys know what the word degree means, but if you guys do not, it means the highest exponent. Let's assume the highest exponent is some value n. I'm using a variable right now, but it's some fixed value. It doesn't change. It is one constant value. Choose that constant value, whatever you want it to be. Is a function, and it's going to have the form of a form. Now, instead of using f, I'm going to use the letter p for polynomial. It is, you can still use f, it's just p is just going to be more intuitive since we're working with polynomials. It's going to be a function p, and our variable, or what it depends on, our input, is going to be a variable x. And what this function is going to do to our inputs, it's going to take x, raise it to your degree n, plus x raised to the next degree minus 1. So if your degree was 6, the next term will be x to the 6th or 5th power. The next term after that is x to the n minus 2 power. And this is going to happen all the way until x to the 1st power plus x, or plus x to the 0th power, which is just a constant. Now, it's going to do all of this to your input, and it's going to multiply each of these by some coefficient. I'm going to call this coefficient a sub n. The n has nothing to do with the coefficient itself. It's just telling you this coefficient is attached to the first term. It is attached to the x to the n power. This has nothing to do with math. All it's there for is so you can match it up with x to the n, which means that we're going to have another constant x to the n minus 1. I'm doing this so I don't use different letters, because then I have to use A, B, C, D, E, F, G, and I could run out of letters depending on how big n is. If my degree was 27, I would have to use all of the alphabet, and I would run out of letters. This lets me use, or notating it this way, allows me to have freedom of all my coefficients. So this is a n minus 2, and it's going to happen till a, or a of 1, and a of 0. And in particular, there's only one, or I guess 2 things that we need to take note of. Your book doesn't say the first thing, but I'm going to note it anyways. The conditions are a sub n does not equal 0. Your first term cannot have a coefficient of 0. If your first term is a coefficient of 0, then you're looking at a different first term, if that makes any sense. So let's say you have x to the 6th power, 0 times x to the 6th power plus x to the 5th. You cannot have this to happen because this simplifies to x to the 5th. So why not just call your x to the 5th your first term right here? Why not call this a sub n? That's the idea. So we have all of this, and in particular, I want you to know that n is a natural number. your degree, your exponents are all natural number. 1, 2, 3, 4. Oh, I guess it's more precise to say whole numbers. We could say natural numbers. Natural. You could say natural numbers, but it's more precise to say, or depending on what term you start off with, you can say whole numbers if you want to include this to be your first term. But I'm just going to say natural numbers for the sake of simplicity, because N for natural. Now, this is what a polynomial form is. It's going to have x terms raised to some exponents times some coefficient. Now, we're going to work with a particular one right now, called the quadratic. We have worked with quadratic equations, and we have worked with the parent graph for quadratic functions. Now, I need to even generalize that even more with functions. So let's call this quadratic, or let me just say a quadratic or quadratic function, I apologize. A quadratic function has the form ax squared plus bx plus c. Your function is called f. It's equal to all of this, assuming again your first term coefficient does not equal 0. This time I can use different letters because there's only 3 different coefficients. If there was more than 26 coefficients, I have to do a sub n minus 1, but that's confusing for students seeing subscripts like that. So I'm just going to use 3 different letters instead of saying a sub 3, a sub 2, a sub 1. You can do it that way. It's just I'm not going to do it right now. So we're just going to say a is not equal to 0. And we know this because if a was 0, then that means your degree or your highest exponent is actually 1, because this would be your leading term. And that's a linear function and not a quadratic. So we have this, and in particular, I want to say that a comma b comma c are real numbers. They're not variables, they're real numbers. You plug them in, or they're actual values that don't change. So that's going to be called, we're going to call this general form. I like to call this general form. Now, there's, this is just a quadratic function, form, but I call it general form because generally it looks like this. Now, in particular, there's another form that we got to learn. This is called standard. And I actually don't like the way standard is used because this terminology was used a while back. I like to actually call it now vertex form. And the reason why I call it vertex form instead of standard form is because it lets you know what the form is used for. Now, back then they called it standard form because this was the form people used for quadratics to always find the vertex or whatever. This was the most common form. But I'm going to call it vertex form so it gives some insights. And vertex form is a quadratic, so your highest exponent is still 2, but I'm going to rewrite it differently. Or I'm going to rewrite it differently. So it's going to be in the form of f of x equals your a times x minus h squared plus k. So this should look familiar to you guys. It looks familiar in transformation, and it should also look familiar in completing the square. All right? I use the letters h and k for a reason because that's what you guys are familiar with when dealing with transformation. In particular, vertex form, we say that the vertex is located at h comma k. The coordinates, h comma k. H is your x value, k is your y value. That is where your vertex is located. So what is a vertex? A vertex is simply, of a quadratic, is going to be where the 2 segments adjoin. So in this case, over here, this is your vertex. And this is located at h comma k, or in this particular one, is located at 0 comma 0. So, looking at this function right here, this function form, we need to be able to tell, or you guys are required to tell me what the vertex is given standard form or vertex form. So, example, what happens if I gave you, suppose f of x equals 3x minus 2 plus 1. Suppose I gave you this function. Where is vertex? Where is the vertex of f? Where is the vertex of my function? Some of you guys might not have a graphing calculator. So how can you find the vertex of f? Well, if you look at our vertex formula, it says that it's just your h and k values. So we have to look at our h and k values over here. But the problem is, this h is negative. It's negative. So when we look at our h and k value, we can say this is plus 1. And then we might think this is minus 2 right here. However, it was minus h. So your vertex is instead located at 2, 1. It's that easy right there. So you have to do the change, or you have to change the sign of whatever value is in your input. Now, for transformation, you can also think of this as, this is how I remember it. This is right 2, and this is up 1. Well, if I go right 2, well, then the vertex should move right 2. If I go up 1, well, the y value of the vertex should move up 1. Because remember, the parent graph, the vertex is located at 0, 0. If I look over here, this is located at 0, 0. If I were to move that vertex right 2 and up 1, I would literally have this vertex. So transformations do have a relationship with vertex of a quadratic. And that's going to be very important. So another one might be, another example I can give is, let's suppose that I go backwards. So another example, instead of me giving you the function, what happens if I give you the vertex? Suppose vertex is -5, 4. And then I ask you, write function, or write the quadratic. I have to specify that. Quadratic in vertex form. Quadratic f. The quadratic function called f in vertex form, assuming f has no stretch / compression / reflections. Now, when I say stretch / compressions, I mean it doesn't have a horizontal stretch, it doesn't have a horizontal compression, it doesn't have a vertical stretch, it doesn't have a vertical compression. When you list these transformations, you have to specify what type of stretch it is, what type of compression it is. You can't just say this has a compression. No, you have to tell me, is this a vertical compression? And what factor? Is this a horizontal compression? And what factor? You have to be specific with that. So, f has no stretch / compression / reflections. How would you write that function? Well, you would start off by saying f of x equals, well, vertex form. Look at vertex form over here. We need to have this form right here. Same as completing the square, kind of. So boom, boom, we have an x over here. Now we got to figure out what h and k's are. They said a, there's no stretches / compression, so your a value is 1, which means we don't even need to care about it. So I can rewrite this as f of x equals parentheses x. Now, this is your h, this is your k. H, k. Your x is your h, your y is your k. Well, it says 4 right here, so we know, this is squared, I'm sorry. We go up 4. Boom. Well, this right here is -5. -5 is left 5. How do I write left 5? Well, that's +5. Or the way you can also think about it, I like to think of in transformations, but some students struggle with that. If this says -5, if you look back to your formula, this says you do the negation. You swap the signs of it. So instead of -5, it becomes +5. I like to tell myself, well, this is left 5. Which way is left 5? It's +5 in my transformations. So this is how you write your function given the vertex. Now, if I said there was a vertical stretch of 3, you would put 3 over here. If I said there was a vertical stretch. If I said there was a vertical compression of 1/3, you would just write 1/3 here. Now, if I said that you had a horizontal compression or horizontal compression of 2, I'm sorry, horizontal compression of 1/2, you would do 2 parentheses this right here. So you have to be careful on what you're doing. You have to be careful on what you're doing. So that covers that. I encourage you guys to try find vertex or find vertex of, let's do find a vertex of this right here, 3x 2x minus 10 squared plus 2. Try to find a vertex of that. A lot of students struggle with this, and I've noticed this on the test chapter 2. Students were not able to find the vertex, or they were not able to find the correct shifts. And I'll give you a hint. It is not 10 comma 2. It is not this. This is not your vertex. This 2 does play a role. Figure out what that role is. So, moving on. Now, what happens? So that's if I give you, if I ask you to find a vertex given vertex form, that should be clear. What is interesting, and this is a question that will pop up on the midterm. I guarantee you it's going to pop on the midterm. So I suggest you practice this. I'm trying to be as transparent as possible what could be on the midterm. So if I were to ask you, find the vertex of x squared. Oops, let me write a function. How about that? Let's call this g of x equals x squared minus 12x plus 13. Find the vertex of this function right here. This is still a quadratic, so it's a parabola. How can you find the vertex? Notice that I expanded out. Instead of having this form right here, I actually applied the second power to it and, actually expanded my problem. So how would you even do that? How would you find vertex form? This is in general form. It's not in the correct form. So what you need to do is put it in vertex form. You need to put this in vertex form. How can you put this in vertex form? Hint. Complete the square. This was in chapter 1, and I know a lot of you guys struggle in chapter 1. I'm hoping by now, it's been a whole chapter. I hope by now that you guys have actually practiced completing the square. So please do not disappoint me on that. Completing the square. And if you haven't practiced on completing the square when everybody has struggled on it, I suggest you do. That will play a major component for the midterm and this chapter. So you have to complete the square in this case. And remember, completing the square states that, hey, I need to find what that perfect square is supposed to be. X squared minus 12x. Now, I'm not going to go and relive about completing the square. We've already gone past that since 2 chapters ago. You guys can look that up again. I'm going to go fast on this, and I'm hoping that you guys refer back to your notes. And if not, come to my office hours. Like I said, the training was off. We're at chapter 3. By now, you guys should know my expectations. I'm not going to teach you guys old content all over again. Otherwise, we get nowhere. So, if I complete the square here, this is going to turn to x minus 6 squared. And then I have to subtract off my square, which is 36 plus 13. Now, this is what g of x is equal to. Now, I can actually combine like terms because this is almost in vertex form. However, I have 2 constant. Over here, there's only a single k. We only have a single k. I don't have k1 plus k2. No, I only have a single k, so I gotta combine like terms. So if I combine like terms now, x minus 6 squared, what is that, minus 23? Now I'm in vertex form. Now I can talk about transformations, or I can talk about where the vertex is located. In particular, the vertex should be located at vertex. I have to change the sign of this guy, so instead of minus 6, it becomes plus 6. So we have 6 for the h value, and then we have minus 23 for the k value. Another way you can think about this is that we move right 6. So from 0, if I move right 6, I better have positive 6. And then I move down 23. If I move down 23 from 0, 0, I better have minus 23 for my y value. So that's how transformation, vertex form, plays a role together. All right, so that's good. So I encourage you guys to try find vertex. Try to find vertex. Try to find the vertex of h of x equals x squared plus 8x minus 2. Actually, I'm not even going to do that. Nope. Let's change that up. Let's do 7x. Boom. Try to find a vertex over here. This might require a bit more work, but you guys can do it. Moving on. Next example. Now we actually bump up the scale in difficulty. We actually have to work with quadratics. Notice that all of these quadratics I worked with, when I completed a square, there was only a coefficient of 1. Now I'm going to change that. This is also going to play a role in factoring. So now instead of doing coefficient of 1, I'm going to do a coefficient of 2. So let's call this capital F of x equals, let's do 2x squared minus 12x plus 13. So now this is a problem. I can't find the perfect square of this guy right here. No, because the coefficient of 2 is in front. And if we try to do that, no matter what we do here, if I try to FOIL this out, I will never have a coefficient of 2 as long as this x is 1, or the coefficient of that x is 1. So that becomes problematic. However, I can still work with it. My key thing, or the key thing in doing these problems, is going back to chapter 1, factoring. I suggest you factor the highest coefficient. Factor leading coefficient. In some books, they say factor out the a value. I'm just going to say factor the leading coefficient out. So if I factor it out, now I'm not going to mess with this guy. This guy I don't mess with. Same with completing the square. With completing the square, I don't even touch that last constant. I only care about working with this part of my function because that's the one where I need to turn into a perfect square. So what I'm going to do is factor out. And I'm going to use brackets so we don't get confused. Brackets x squared minus 6x. And then plus 13 is all the way at the side. I don't care about that guy. Well, now, this is a perfect square. This is a perfect square. So, instantly you should tell yourself, complete the square. Complete the square. So, complete the square states that, hey, this is going to be exactly 2 times x minus 3 squared. 2 times x minus 3 squared. However, remember, technically speaking, if we wrote our perfect square, this should have been x squared minus 6x plus 9. Right? That should have been plus 9, but it's not. I lost the 9. I lost the 9. So, I have to subtract off 9. But, if this was missing a 9, notice that I'm also multiplying that by 2. So you have to do a bit more. You have to subtract off what you're missing, and you got to multiply it by your leading coefficient, which is 2. Boom. So you have this function over here. This is going to be your capital F of x. And then if I combine like terms and simplify, I get capital F of x is equal to 2 times x minus 3 squared minus 18 plus 13. Combine like terms. X minus 3 squared minus 5. So now that I have it in this form, I can write what the vertex is located at. The vertex is located at 3 comma negative 5. Boom. You could even go further. If I were to ask you what are all the transformation, you would say right 3, down 5, and you can also say vertical stretch of factor 2. So you can do all of this stuff. This is very nice. So now I encourage you to try this out as an exercise. Try out 3x, let's call this capital G of x. Try find vertex of capital G of x equal 3x squared plus 12x minus 8. So once you have practiced these and got the hang of it, now we can talk about minimums and maximums. Min slash maximums of quadratics. Now, the minimum and the maximum of a quadratic is always going to be your vertex. Excuse me. It's always going to be your vertex. So, if I were to draw it out, you can either have your parabola looking like this, or if I reflect it across the x-axis, and I hope you guys remember how to reflect across the x-axis, and what that means algebraically for transformations. If you were to reflect it across the x-axis, well, then you get this. Which one is a minimum or which one is a maximum? This is a minimum. Oops, the vertex over here. It's located over here. This is a minimum. This is a maximum. You can say local max, you can say local min. Actually, these are just the minimum and maximum. These aren't, you can say locals, but they're actually your legit maximum and minimums. So, how do you know if they are maximums and minimums without looking at it graphically? Well, if your leading term is bigger than 0, you have a minimum. If your leading term is smaller than 0, you have a maximum. So, in that case, to calculate your minimum and maximum, all you have to do is calculate your function, evaluate at h equals k. What does this mean? This means that wherever your vertex is, the x value of your vertex is going to be the x value of your maximum min. But to calculate your max and min, you have to plug in the h, or your x value for your vertex, into your function. Once you plug it into your function, you will get your minimum, you will get your maximum. And this is why when I was grading key features, I wanted everybody, when they're calculating maximum, local max, and local min, to only list the y values. When we talk about maximum mins of an actual real world problem, we're talking about the height. We're not talking about anything else. So, let's try an example. Let's say I wanted you to find the minimum of 50x squared minus 30 minus 30x plus 49. I know this is a minimum because this value is 50 is clearly bigger than 1. 50 is clearly bigger than 1. So let me fix that up. 50 is clearly bigger than 1, so I know I have a minimum. Our quadratic, normally it is a parabola that's open upwards. And when it opens upward, it has a minimum. So, where is my minimum located at? Well, all you got to do is calculate it using completing the square. So complete the square says that you have to do, well, this one's a bit more work. It's a bit more work, but it is still doable in this case. So what you would, oh, why did I have 50? This is supposed to be a 5, I apologize. Boom. So it should be a 5x. It's less work now, but same idea. You have to do complete the square. Well, complete the square say that first I have to factor out that leading coefficient. X squared minus 6x. And then don't mess with that 49. Do not mess with it at all. Don't play with it. Now, after I did that, what I need to do is complete the square. So this is automatically going to be x minus 3 squared. I'm going to subtract off whatever I square times my leading coefficient 5 plus 49. So now we get 5x minus 3 squared minus 45 plus 49. 5x minus 3 squared minus 40. Or it's going to be plus 4. Boom. And this is my new function right here. So boom. So my vertex is located at 3, 4. So my my minimum is equal to 4. That's one way to do it. There's other ways to do it. We'll discuss that in a bit. Now, that's how you can find maximum minimum. Or if you actually follow our rule here, if we plug in h2f, if we plug in this value to my function, what that means is if I did 5 times 3 minus 3 squared plus 4, I am going to get 4 out. Let's actually calculate that out. 5 times 0 squared plus 4. And then 0 times 0 is 0 plus 4, which is going to be 0 plus 4, which does give me the k value. F of 3 equals 4. If I plug in 3 to my function, I do get 4. So let's call this F. Boom. So it does work. If I plug in my value, boom, you're good to go. Now, this is, you might ask yourself, why am I doing even this to calculate my k when vertex form tells me the k? Clearly this says 4, so why do all that math to get 4 down here? Why do all of that math? Well, because there's different ways to calculate vertex. Sometimes you don't even have to complete the square. You can do parts of completing the square. And we're going to get to that in a bit. So now let's do a maximum one real quick, just to be sure. We have negative x squared plus x plus 2. Well, my coefficient is negative 1. Factor out a negative 1. Get x squared minus x. Don't mess with that plus 2. Leave it all the way over here. It lives on an island. Boom. Now, I have to complete the square. Well, this is technically a 1 here. So this becomes negative 1 times x minus 1 half squared. Now, we got to square that value. So that's going to be minus 1/4 times negative 1, which is our coefficient here, plus 2. After that, we can simplify everything. We got negative x minus 1/2 squared. This is going to be plus 1/4 plus 2, but we have to add fractions together. So this is going to be 8/4. And then we're going to get, what function did I call this? Let's call this g of x. We're going to get g of x equal negative x minus 1/2 squared plus 9/4. This means, in transformation, it means we reflect across x, we move right 1/2, and we move up 9/4. In terms of vertex or maximum or minimum, this case is a maximum because there's a negative here. This negative 1 is smaller than 1. Boom, by our little rule up here that we've stated. So what this means is that our maximum is located at 1/2 comma 9/4, which is the vertex as well. So the max is 9/4, and this is the vertex. And then lastly, I hinted at other ways to calculate your maximum. And the idea is not to actually calculate all of the vertex, or you are still calculating vertex, but it's not to actually do all of completing the square, but you can only do half of it. Technically speaking, if you do half of completing the square, you can easily find your max. You don't have to express this entire function over here as a perfect square like this. You don't have to do all of that work. There are easier ways. So if you're more comfortable with this way, then boom. I still expect you guys to be able to complete the square for specific problems. However, if I generalize just finding the max and mins, you're able to do this, path instead. So, finding max / mins. Well, there's a little formula for that. We're going to say the x value of max / mins / vertex is, it's going to be negative b over 2a. Or, let me be more precise. It's not just x. I could just say this instead. Let's say h. That's part of your vertex. That's the x value for your vertex. Your maximum minimum is located at negative b over 2a. So, that means the max / min is going to be equal to your function evaluated at your x value. if I throw in my input into my function, I should get the y value, or I should get the output, which is my maximum or minimum. Boom. So if we take an example, let's say, and you can verify this later on, but let's say I have 3x squared minus 2x plus 1, and I just wanted to find the max, or find minimum. I know it's a minimum because this value 3 is bigger than 1. So find the minimum. Well, all you have to do is find h right here, which is negative b over 2a. So let's go ahead and do that. Negative, and then b, which is negative 2, over 2 times 3. Which that's going to give me positive 2 over 6, which is going to give me 1/3. So your h value, we already have part of the vertex. The vertex is located at 1/3. We need to figure out what that last value is. And to calculate that last value, do f of 1/3, which is going to give me, let's see, 3 times 1/3 squared minus 2 times 1/3 plus 1. If I calculate this, I have to do the exponents first. So if I do 1/3 squared, I get 1 over 9 minus 2 over 3 plus 1. And then this is going to give me 3 over 3, or 3 over 9, I apologize. 3 over 9 minus 2/3 plus 1, which is going to give me 1/3 minus 2/3 plus 1. And this is going to be negative 1/3 plus 1, which is going to give me, what is that? 2/3. So I have that. That means my minimum is located at or my minimum value, minimum is equal to 2 over 3. It's located at 1/3, comma 2/3, but if I just ask you for the minimum, you got to give me the y value, which is 2/3. So be sure you're able to do that. And then I encourage you guys to look at the word problems listed in your book. That way you have more practice on this, because if you see word problems and you see the word maximum or minimum, you should instantly think of finding the vertex. And that's the end of today, so I will catch you guys later. Take care.